The structure of the Sun. When viewed from Earth, the Sun appears as a massive, hot sphere. However, its structure is highly complex, and it is essentially a gigantic ball of gas. The Sun's structure is divided into 4 main layers. 1. Core. The core of the Sun is the central part of its structure and the source of its energy production. It is the hottest and deepest region of the Sun, where all the energy is generated. The characteristics and processes in the Sun's core are as follows. Composition. 1. The core is a dense, hot, and highly pressurized gaseous ball composed primarily of hydrogen, about 70%, and helium, about 28%. 2. Due to the extreme temperature and pressure, hydrogen atoms fuse together to form helium atoms. Temperature and pressure. 1. The temperature in the core is around 15 million degrees Celsius, 15 million degrees Celsius. 2. The pressure is extremely high, approximately 340 billion times Earth's atmospheric pressure. Nuclear fusion. 1. Nuclear fusion occurs in the core of the Sun, which is the primary source of the Sun's energy. 1. In this process, hydrogen atoms fuse to form helium atoms, releasing enormous amounts of energy in the form of heat and light. 2. The main reaction, 4 hydrogen atoms fuse to form 1 helium atom, releasing energy. 3. This energy is then transmitted to the Sun's outer layers, providing energy to the entire solar system, including Earth. Energy production. 1. The energy produced in the core takes a long time to reach the Sun's outer layers. 1. First, it flows through the radiative zone, then through the convective zone before reaching the surface. 2. This energy release creates the Sun's heat and light, which is vital for warming Earth and sustaining life. Conclusion. The core of the Sun is the primary source of its energy production, where nuclear fusion occurs. This process ensures the distribution of energy throughout the Sun and is an integral part of its life cycle. The energy produced in the core is the main source of heat and light for our solar system. 2. Radiative zone. The radiative zone is the layer just outside the Sun's core, where energy is primarily transported in the form of radiation, light waves. This zone plays a crucial role in transmitting the energy produced in the core to the outer layers. 1. Location. The radiative zone is located just outside the core and extends up to about 37% to 45% of the Sun's radius. It is the largest part of the Sun's interior. 2. Temperature. The temperature in the radiative zone is much lower than in the core, around 2 million degrees Celsius, 200 million degrees Celsius. 3. Energy transport. In this zone, energy is transported by radiation, in the form of photons, light waves. The energy produced in the core first exits as photons and bounces off particles in the radiative zone, slowly making its way to the outer layers. This process is extremely slow, and theoretically, it can take hundreds of thousands of years for energy to travel through this zone. Conclusion. The radiative zone is an important layer of the Sun's interior where energy is transported through radiation. This slow process allows the energy produced in the core to gradually move to the outer layers, contributing to the distribution of the Sun's energy and light. 3. Convective zone. The convective zone is the layer outside the radiative zone, where energy is transported through convection, a process where heated gases rise and cooler gases sink, creating a convection current. 1. Location. The convective zone is located just outside the radiative zone and extends to about 30% to 50% of the Sun's radius. 2. Temperature. The temperature in the convective zone is much lower than in the radiative zone, ranging from about 200,000 degrees Celsius to 500,000 degrees Celsius. 3. Energy transport. In the convective zone, energy is transported by convection. Hot gases rise toward the surface, cool down, and then sink back down, creating a cycle. This ensures efficient energy transport to the Sun's outer layers. 4. Convection cells. The convective zone contains small solar convection cells, which appear as solar cyclones or convection cells on the Sun's surface, contributing to the formation of sunspots. Conclusion. The convective zone is crucial for energy transport in the Sun, where convection currents move heat and energy from the inner layers to the outer layers. This process ensures the generation of heat and light at the Sun's surface. 4. Solar atmosphere. The Sun's atmosphere consists of its outer layers, beyond the surface, where various phenomena occur, such as solar storms, solar wind, and other energy and heat transport processes. The solar atmosphere plays a direct role in sending energy and light from the Sun to Earth and other planets. The main layers of the solar atmosphere include photosphere. 1. The photosphere is the visible surface of the Sun from which light and heat are emitted. 1. It is the outermost layer that is visible to the human eye. 2. The temperature is approximately 5,500 degrees Celsius, 5,700 Kelvin, and this layer is the primary source of sunlight. Chromosphere. 1. The chromosphere is the layer above the photosphere, seen as a reddish glow during a solar eclipse. 2. The temperature here is slightly higher than the photosphere, around 20,000 degrees Celsius, 20,000 Kelvin. Corona. 1. The corona is the outermost layer, a hot, plasma-filled layer that is much hotter than the Sun's interior. 2. The temperature in the corona is about 1 million degrees Celsius, 1 million Kelvin. 3. The solar wind, a stream of charged particles, emanates from the corona and spreads throughout the solar system. Characteristics of the solar atmosphere: solar storms. 1. Solar storms can cause powerful electromagnetic waves and affect Earth's magnetic field. 1. These storms can disrupt satellite communications, power grids, and telecommunication systems. Solar flares. 1. Solar flares are massive eruptions of energy from the Sun's atmosphere, causing intense bursts of radiation and magnetic activity. 1. They can have significant impacts on Earth, such as affecting telecommunications and triggering geomagnetic storms. Solar wind. 1. Solar wind is a flow of charged particles from the Sun's corona that spreads throughout the solar system, influencing space weather and contributing to phenomena like the aurora borealis. Conclusion: the solar atmosphere is an essential part of the Sun's structure and energy process, playing a direct role in the transmission of energy and light to Earth and other planets. The photosphere, chromosphere, and corona provide valuable insights into the Sun's behavior and its effects on the solar system. Conclusion of the Sun's structure: the Sun is an essential and central part of our solar system. Its structure is highly complex, and its energy production process remains one of the greatest mysteries in space science. The Sun generates energy through nuclear fusion in its core, where hydrogen atoms fuse to form helium atoms, releasing massive amounts of energy. This energy then travels through the core, radiative zone, and convective zone before reaching the surface, where it is emitted as light and heat. Each layer of the Sun has a unique temperature and density, which maintains its energy production and functioning. The Sun's energy is crucial for sustaining life on Earth, and studying the Sun provides valuable insights into the structure and behavior of stars throughout the universe.